This lesson is on electrolytic cells. All right, so we're going to go back and review what happens when we have a metal. So here we have a blown up picture of our metal showing a valence electron on each metal. So we know that the valence electrons are localized or mobile. And when we apply a voltage, then if we have an electron that comes in, all the other electrons adjust and we will get an electron that comes out. But we don't just have one electron going through our wire, we have a bunch of electrons. And if we were to count the electrons that go through in a second, multiply by the charge of the electron, we would get the total amount of charge that crosses a particular point in a second. And we call that the current. The current, and we represent that by capital I. And this is the charge per unit time. So our I then equals, the charge is Q, and remember that's 1.602 times 10 to the negative 19th coulombs for the magnitude of an electron. So Q over T. So our units, the unit of charge is C, the coulomb, and time is the second. So coulombs per second is the unit of current, how much charge is being carried through the wire in 1 second's time. And that unit is called the amp, short for ampere. So we can answer such questions as, what is the charge for a 3.5 amp current running for 8 minutes? So in electrochemistry, whenever you see amp, it's a good idea to write that as a coulomb per second because that is in the conversion factor form. So 3.5 amps, that is 3.5 coulombs for every 1 second, the charge per second. Okay, so we're just going to use dimensional analysis for this. So our charge, so XQ equals, or our quantity of interest is 8 minutes, 8.00 minutes. Now we have seconds for our current, so we're just going to change those minutes to seconds. So 1 minute then is 60 seconds. And now we can use our current conversion factor. So we have 3.5 coulombs for every 1 second. So minutes cancel, seconds cancel. We're looking for Q, which is coulombs. I guess I should have put X coulombs for charge. Okay, so we get 8 times 60 times 3.5 equals, and so we get 1680 coulombs. That has 2 sig figs, so to write that with the proper sig figs, that'd be 1700 coulombs. And I should have had coulombs there, X coulombs, even though charge is represented by Q. All right, so that was just a little intro before we get to our topic of electrolytic cells. So if we take electrochemical cells, they get broken down into 2 types. So we've already done galvanic, and sometimes galvanic cells are called voltaic cells. And then the other type that we're going to concentrate on today is electrolytic. Now, we've already seen that a galvanic cell is spontaneous, the reaction for it, and the electrolytic then is non-spontaneous. In our galvanic cell, chemical energy is transformed into electrical energy. You can light light bulbs, light flashlights, do all sorts of things. And in an electrolytic cell, it's the opposite. We're going to take electrical energy and transform that into chemical energy. In our galvanic cell, we have a negative delta G, because if it's spontaneous, the delta G has to be negative. In the electrolytic cell, we're going to have a positive delta G. For our galvanic cell, we have a positive E of our cell, and for the electrolytic, we will have a negative E for the cell. In our galvanic cell, the current naturally flows. And in the electrolytic cell, we're going to force the current to flow. Force the current to flow. Okay. So we're going to go back and look at our zinc copper cell in terms of having a galvanic cell and then the difference when we have an electrolytic cell. So we've already seen this galvanic cell. So we have zinc and copper. 1 molar zinc nitrate, 1 molar copper Roman numeral 2 nitrate. The zinc gets oxidized, and our E0 of the oxidation, we have to flip the sign from our chart. We get 0.76 volts. The zinc is the anode, and this is the anode compartment. On this side, the copper ions come up to the copper electrode. They take 2 electrons and get reduced into copper metal, and our E0 is 0.34 volts, giving us a positive 1.10 volts. And we could calculate the delta G0 for that using minus NFE. So our anode, our electrons flow out of the zinc and into the copper. Now, in an electrolytic cell, we have to use a power supply, and we're going to force the current to go from the copper to the zinc. So when you have a galvanic cell, here you'll have a voltmeter or a light bulb, something that lets the current flow. Here we have a power supply, a powerful battery, more powerful than our zinc copper reaction, that's going to force our electrons to go the other way. So our power supply is going to make the current flow this way. So for this to be able to happen, the voltage of the power supply must be greater than the E of the cell. So if everything's 1 molar, the voltage has to be greater than 1.10 volts to force the current to flow in the opposite direction. So here, now, we're making the zinc get reduced, so we're going to reverse everything. So over here, the zinc ions are going to take the electrons and become zinc metal. So the zinc becomes the cathode. You always have reduction at the cathode, no matter what type of cell you have. Cathodes are reduction. Cathodes are reduction, anodes are oxidation. So here, our power supply is forcing the copper to give up its electrons and be oxidized. So now the copper is the anode where we have oxidation, and the this compartment is the anode compartment. So you might want to do this if you want to plate something with zinc. So the E0 of this cell then is negative 1.10 volts, because it is the opposite of this cell and this equation. So our equation for this cell is the opposite of this. It's Zn2 plus Cu goes to Cu2 plus Zn. So this does not happen naturally. we have to force it to happen. All right, and we can answer questions now based on this electrolytic cell. So again, you always want to look at what's up here. Is it a power supply that's forcing current to flow, or is it a voltmeter that's just measuring the voltage? Okay, to do the problems that we're going to do, you want current, always write it as coulombs per second. That's going to help with our dimensional analysis. For EMF, it's in volts. Write that as joules per coulomb, the energy per charge. And then don't forget we have Faraday's constant, which gives us the charge for 1 mole of electrons. So keep these three in mind for when we do problems. All right, so here's an example of a problem. How many grams of zinc can be plated with a 5.00 amp current running for 20 minutes? And we're referring to the electrolytic zinc copper cell that we just went over. All right, so again, this 5.00 amps, that means that we have 5.00 coulombs of charge for every 1 second that's going through our wire. Okay, so we're just going to do one big dimensional analysis. So X grams of zinc equal, our quantity of interest is 20 minutes, 20.0 minutes times, we got to get this to seconds, so 60 seconds in 1 minute. All right, so now we can use our conversion. So we have 5.00 coulombs for every 1 second, crossing out the seconds. Now we're going to use Faraday's constant because when we get the electrons, that's going to get us to the zinc. So we know that 1 mole of electrons has 96,500 coulombs. Okay, so now we have moles of electrons. Where do we go from here? Well, if we look back to our cell, we have the zinc ions plus 2 electrons go to zinc. So we have 2 moles of electrons for every 1 mole of zinc that gets plated. 2 moles of electrons for every 1 mole of zinc. So that is our conversion. For every 1 mole of zinc, we need 2 moles of electrons. Moles of electrons cancel out, and now we just got to change those grams to moles. And where is my molar mass of zinc? 65.39 grams of zinc in every 1 mole of zinc. So all our units have canceled out except for the units we want, which is grams of zinc. Sig figs 3, unlimited 3, 3, unlimited 4, so 3 sig figs we need for that. So 20 times 60 times 5 divided by 96500 divided by 2 times 65.39 equals. All right, so we get 2.03 grams of zinc get plated onto the zinc electrode when we have 5 amps of current for 20 minutes. Okay, let's do another one of these. All right, so now how long does it take to plate 2.5 grams of zinc with a current of 7.8 amps? So this means that we have 7.8 coulombs of charge every second. All right, X, how long? Doesn't tell us what units, we'll just use seconds. So X seconds equals, our quantity of interest is the amount we want to plate. So that's 2.5 grams of zinc. Change those grams to moles. So 1 mole of zinc is what I said that was, 65.39 grams of zinc times, Now we need to get to coulombs, so if we can figure out electrons, then we can get to coulombs. So for every 1 mole of zinc that gets plated, we need 2 moles of electrons. So 2 moles of electrons for every 1 mole of zinc. Cancel out everything we can cancel out. All right, so once we get to that, now we can use our Faraday's constant conversion factor. So 1 mole of electrons carries 96,500 coulombs of charge. Moles of electrons cancel out. And now I can use my amp conversion factor. So for every 1 second, there is 7.8 coulombs of charge that gets carried. So everything cancels out except for seconds, the unit that we want. 2 sig figs, 2 sig figs. So 2.5 divided by 65.39 times 2 times 96500 divided by 7.8 equals. And we get, let's see, 2 sig figs, so that's going to be 950 seconds. Let's see, if we wanted minutes, that would be 16 minutes. But it didn't ask us, so that's fine. All right, so don't forget your moles of electrons. You get that from your reduction half reaction. Faraday's constant, change amps to coulombs per second. And if you have volts anywhere, change that to joules per coulomb. And that's it.